So I will present you some elements about sustainable mobility and more particularly the impact of the steel types used in this solution. The point I wanted to make was, of course, that transport is responsible for about 25% of the greenhouse gases. And it's clear that it needs to be decarbonized. And we, as a steel company, are very keen on bringing our part of the CO2 reduction into the world, and therefore are an active participant in the clean energy transition. We've been working very hard on these aspects of green electrification. First of all, a while ago, when there were all the renewable electricity generation systems coming up, and afterwards also for high power density machines, and they are used in the electrified transport today. Just to make sure that you can see me, I guess I should start my video, but somehow he doesn't want me to do that. My apologies.
I will check, but you can go ahead.
Yes, exactly. So the point that I wanted to make is also that the electrification of transport, of course, everybody knows about electric vehicles, but then there's also the aspects of green cargo transport. And they are a challenge both on land, on sea, and on air, mainly because of the battery capabilities that are limited for these kinds of large weights that need to be shipped. So, oops, now I have a problem with moving my slides. What's happening?
Yeah, maybe you need to stop sharing and try it again.
Yeah, I will stop sharing and then see if I can already get the camera on. No, he absolutely doesn't like me putting the camera on.
Okay, you can maybe try to share.
Yeah, I'll try
your
to
screen.
Share.
We will see the camera for Q&A. We can focus on the slides now.
Yes, indeed. Let me share my screen again. And go back to the presentation mode.
Yeah.
Yeah, this is better.
It works.
So, yeah, sorry about that. So the particular transport system that I want to present to you today is about hyperloop technologies, and mainly because they are a very relevant solution in terms of green high-speed transport in between what's happening on the high-speed train activities and also the electrification of airplanes. The hyperloop systems obviously need electromagnetic systems inside of these tubes for propulsion, braking, levitation, and guidance. And this presentation will in particular focus much more on the propulsion system. The importance about these electric systems is, of course, that they need to be with a high efficiency level. We want to do energy recuperation to improve the efficiency. And apart from that, the hyperloop system is also relevant to reduce dust, noise, and there is no physical contact during the transport, and therefore it also reduces the wear that you have in normal transport systems. So it has certain advantages that are certainly worthwhile looking into. I think I've already explained some of these aspects, but what I didn't say so far was that the hyperloop technologies use linear motors that are exposed to very high force levels in a pulsated way. So these linear motors are exploited in a completely different way than what you see in an electric car. And the control mechanisms are also very, very difficult to realize because you need a very tight control, and that is in particular the case for the levitation systems. So it is important to look at such a system on its whole to make a perfect combination between the ferromagnetic materials that are being used, the mechanical properties of these materials, and also to create the right thermal balance, as we saw in the previous presentation as well. So I'm going to talk a little bit more about the use of linear synchronous machines for hyperloop. We've been calculating a machine that is with a wound field system. This is in particular because we prefer to work on systems without permanent magnets and in particular without neodymium magnets, in order to assure that we're not coming into the trap of creating a system that is using critical rare earth materials, as Fernando was saying in the introduction of this conference. So this is the specification of the motor. We want to have a propulsion force of 110 kilonewtons, which is coherent with the needs of a pod that is proposed into the tube and that moves at the speed of maximum 1,000 kilometers per hour. In terms of the electrical steels that we're looking at for the stator and the mover, we've worked with very basic steel and these calculations, 0.65 millimeters, just to show the importance of making the right steel selection. And in the first result of a study we did previously, we were checking how it would be possible to connect these electrical machines into the tube and how that would influence the performance of the machines. So you can see here a possibility of using either a dovetail connection system on the stator side, this is the mover side, or working with a plate that is at the back of the stator. When we did the first calculations regarding the losses, so the Joule losses that are happening in these fixation systems, we saw that this classic connection system of a dovetail is really not the best one to choose because you get a higher level of losses. And we had also looked, first of all, whether it was relevant to use either carbon steels or austenitic stainless steels for these connection system. Of course, with the austenitic stainless steel, you will create a shielding effect. With the carbon steel, you have the potential of having more eddy currents circulating in this backplate. And that's indeed what we find when we do the calculations. So let me go to a little bit more detail about the content of this study. So we're now looking at a tube, which is here this side. You have the linear motor here, and we're checking on how this system should be integrated, because the problem is, of course, that you create a lot of electromagnetic fields here in the stator stack, and then they can just disappear into the, well, this is first of all the housing, it's a U-profile shape, but then it can create a flux that goes straight to the tube, and therefore it's not bringing any advantage to the system. And therefore the mechanical integration is first checked according to the different standards that need to be applied. And remember that we have very high forces that come through when the pod is passing by, and we assured that the whole of this connection system is going to be resistant to the mechanical forces that we want to apply from the machines. We've done this with a bolt connection through the stator stack and through the stator housing. And we will now go into a little bit more detail on how such a stator stack can be built. First of all, there is this point. We're going to create a system with 30.5 megawatt of power, which is quite big. And we need to model the losses. First of all, you can see here some work we did with the two-dimensional modeling. And it's clear that we need input data from the materials. We've done the magnetic measurements on these materials according to the IEC standards. That's mainly resistivity and permeability as an input point, first of all, for the losses, and here also for the force calculations. The results that I wanted to explain are, first of all, again, what is happening inside of the supporting structure, depending on whether it's being fixed by using stainless steel. In this case, it's austenitic stainless steel, or by using carbon steel. And then the next step, of course, in the integration is the fact that we need to put in these bolts, and therefore you have holes in the system and you create a distortion of the magnetic flux. We first of all checked best position to place these holes, and then looked at the impact such holes have on the creation of the required force level. You can see it's not all that important. What is important is the Joule losses you have here in the backplate, and they are quite different between stainless and carbon steel, as we saw before, without the presence of the bolts. Please note that we used here oversized holes for the bolts because we wanted to see the effect of the contact that is made between a bolt and a hole. And that is the next aspect. We will always have some sort of misalignment because this is a very big construction. There will be some tolerances that are needed in order to be able to build it. And therefore the bolt is never going to sit in the center of the hole. So we looked at the different possibilities in terms of oversizing the hole, in terms of putting the bolt in an eccentric position, and whether there is or not is not going to be a contact. And I'm sure it's very obvious, but here we have it quantified that the losses are sort of doubling or even tripling when you go into the contact position, which is definitely important to avoid. And the other point that is already interesting to see, that if there is just a misalignment, then it's not that bad. It's really the contact that makes the biggest problem in terms of the flux redistribution and the loss creation. The next step is when you want to build such a system is that, of course, you cannot create meters and meters of electrical steel stacks that are going to be necessary in the whole length of the tube. So therefore, you will have to work with a segmentation, and that creates a parasitic air gap. Like the same way when you have a rotational machine, you could also work with segments and you would have parasitic air gaps between the segments. Here, the parasitic air gaps are first of all assumed to be 0.5 millimeters, just to cover for the basic linear expansion. In practice, they can be bigger if you want to be sure that you cover for all the construction tolerances. So first of all, we made this calculation for 0.5 millimeters, and it should be clear that the Joule losses are obviously, again, increasing when we look at a carbon steel backplate. That the fact that we create this segmentation with just 0.5 millimeter doesn't really impact the total force that is being developed. But the point is really that you have an increase in losses. What you're doing, the way we've drawn it here, is you create, in fact, the flux to go through the backplate at these moments of segmentation. So in this case, the housing is like a continuous profile and the stack is interrupted. There could be other possibilities of building the construction where you would also interrupt the backplate here. And then, of course, the situation would be different. But again, it's important to realize how the flux patterns are going to change when you have to make these construction measures. Then let's now look at the total losses of the system. First of all, it's interesting to see that on the mover side, the most important part of the losses are the copper losses, which is in fact quite logical. They are occurring with higher frequencies because you have the harmonics, and therefore it's not surprising that you have on the mover side much more copper losses than you have on the stator side. Then if you look at the division on the core losses, you see that we get this very high eddy current loss level on the stator side. And that's because we've got a machine which has a high magnetic loading, and the thickness of the electrical steel was 0.65 millimeters. And therefore it's very clear that this is not an optimal choice if you want to build this kind of machine. So I've gone through the presentation quite quickly. I've tried to explain you how a linear synchronous propulsion machine can work for a hyperloop infrastructure, to show that you have to make many more calculations than the basic assumptions that you can would start with. It's very important to consider the integration part, to look how you will fix it, what is going to happen with the surroundings of the motors, how you will assemble the laminations, how you will put them in the stator housing, and that you take care about every single aspect of this construction process. It's important to realize where the stray fluxes will go to, and it's also important to put stainless steel parts there where you are going to have a problem of fluxes going into stray parts of your construction. The aspects that are very important to take away from this presentation is that it's really relevant to check all the different steel types that exist and that can be certainly used for these hyperloop systems, the very particular steel choices that we have available, because very often it is thought that those linear motors can be quite basic and therefore you can just use basic steel types, but absolutely that is not going to bring you the best high efficiency solution. And it's clear that hyperloop can only become a relevant solution for the future if the global energy performance is good and even better than the existing solutions of today. So that was my presentation, and if you have further questions, I'm happy to